Okay, so what I want to do in the next, I hope, 30 minutes is to give you a kind of a summary of the Chapter 6 material. And the entire, well, mostly the point of Chapter 6 is to explore an idea that is the first idea in the interpretive statistic chapters, where we need to be able to use sample data to create an estimate for a value of the population parameter. And we actually do this quite a lot. One of the things that we will do is look at estimating a population proportion. And so think election polls, right? Because what essentially election polls are is an estimate from a sample of what we expect the true proportion of people to be that vote for a certain candidate. And we can't estimate that exactly, right? What we try to do is get really good sample data and then use that data in a statistically appropriate way to develop a range of numbers within which we expect to find the population proportion that support a specific candidate. So what a confidence interval is a range of numbers, right? The center of the range of numbers is either p hat, the proportion in a sample, or x bar. And then the distance from the center to the lower edge is called a margin of error, which we use the symbol capital E for that. And then when we add a margin of error, we get to the highest number in the interval, a large confidence estimate of where the actual population proportion or mean is. And we're only going to deal with these two particular population parameters. So this range of numbers we expect to actually include the population parameter of interest. Now, again, there are two types of intervals that we're going to be dealing with. The first one is the mean in a population. Well, you know, say let's say we wanted to estimate what the average salary was of college professors in our area. Well, we can do that, and one of the things that we would need to do is get a statistically reasonable sample data for the salaries of any of the professors in our region, and we would try to do that in a purely random way to make the data more reliable. And we would need to take a number in the sample that was large enough, again, for the estimate to be reliable. In any case, if we're trying to estimate the value of a population's mean, then the symbol we're using is mu, because that's the symbol for population mean. But the estimator we will use for the center of the confidence interval is x bar, the sample's mean. And it's important to note here that one of the things we have done is omit the very first section of this chapter, but you really ought to read it. We omit it because it deals with making a confidence interval when we have specific knowledge of the standard deviation of the underlying population. Since that doesn't, on a practical basis, happen very often, we will instead go directly to section 6.2. And the difference between these two is if you know the standard deviation of the population that you are trying to estimate the mean for, you get to use our regular old standby Z distribution, that normal distribution table. Because we are not assuming that we know the standard deviation of the underlying population, we're going to have to introduce a new distribution. It's very similar, but we need a new table to make to use the T distribution. And I'm not going to say a lot about the differences between the normal distribution Z and the T distribution, except to say they're both bell-shaped, but the t-distribution varies slightly in its shape when it is at low sample numbers, like numbers under 30. In any case, they do deal with this in much greater detail in your chapter 6.2, and that's on page 310. But suffice it to say, for our practical purposes, we're using a z-distribution whenever we're estimating a confidence interval around a population mean. And the one new skill we'll have to acquire is being able to find a critical value using the t-distribution table. Not hard, though. The second type of confidence interval we want to make is an interval around the estimate of a proportion, like an election poll. And to do that, we need another estimator, and that estimator is going to be p hat, which is the proportion that we found in our sample data. And in this case, we can use that regular normal distribution table that we used previously doing the probabilities. Now, one thing you have to understand about confidence intervals is that you have a choice of how confident you want to be, okay? And the determination of that choice changes a thing that we call the critical value, and critical values are used in creating these confidence intervals by using the formulas, okay? Now, we're going to emphasize mostly the technology and mostly StatCrunch here. In that case, you don't have to look up the critical value, but I'm going to show you how to do it using the formulas. So the determination of a critical value using either the bell-shaped z-distribution or the bell-shaped t-distribution. That is important if you're using the formulas. And that is something that is determined by how confident we want to be. So how should we envision a confidence interval? So if I choose a confidence level, and here I've shown a 90% confident, what it means is that I want to be 90% certain that that range of number actually includes the true value of the population proportion. So let's say we're talking about mean. What I'm saying is if this center is X bar, I want to make sure that between these two ends, the range of values includes the true population mean, which is mu. Now, if you think about it being centered on a bell-shaped curve, which both the z and the t distributions are bell-shaped, then what you have is an area to the left and the right, and I'm going to label those as alpha divided by 2. So alpha, I mean, casually, I like to think of it as uncertainty. Okay? So what we're really saying is we want 90% of the time to have an interval that will include the true population's value, whatever that parameter is. Here I'm using the example of mean. But we know that it is possible to be wrong to the low side or wrong to the high side. And so the critical values are actually the values of z or t that split this into the area of the confidence interval and leave these areas of uncertainty to the lower or the high side. And you can see that if I have a confidence level that were 95%, and I'm just going to put ... here, to get to 95%, my interval would have to get wider, right? My z or t values would change, and the size of my uncertainty would be smaller as well. So this is the kind of picture you should have in your mind, because we're going to look up some of these t and z values and use them in the formula, but what they represent are the barrier numbers that separate out the selected confidence level centered on the bell-shaped curve from the areas of uncertainty to the left or to the right. Okay, so I want to really emphasize that skipping that one section gives people some trouble. But what you should remember is that if you're trying to find an interval around a mean, you are going to use T distributions, because we're not assuming that we know the value of the population standard deviation. And if you're trying to find a confidence interval around a proportion, then you're going to use a Z distribution. But on StatCrunch, it is labeled. StatCrunch labels these things as proportions. And so I'm going to show you a picture of a StatCrunch page here, okay? Notice that when we do this using StatCrunch in a minute, we have the choice of Z-stats, T-stats, proportion stats. What I'm explicitly saying is you're not going to use this thing called Z-stat for either the mean or the proportion intervals. You're going to explicitly be using the T-stats area for means intervals and the proportion stats area for proportion intervals. Now, when I looked at the results of the previous final exam in the spring of 2019, this was a very common error, okay, because the Z-stat area will seem to be able to give you a confidence interval, but you have to emphasize that when it's a T-stat, what you are putting in is the sample mean and the sample standard deviation. If you look closely at the area called Z-stat, it actually says the population's standard deviation. Okay, so you have to be careful about use of StatCrunch here. All right, so then how do we do it? So the formula for doing a confidence interval around a mean when you do not know the standard deviation of the underlying population is to calculate the margin of error, okay, and that is equal to a critical value of T times the standard deviation of the sample divided by the square root of the size of the sample. Okay, so here's what we've got. We've got a sample. We're going to assume that it has been gotten in a statistically appropriate way. We know the size of the sample. We know the mean of the sample, and we know the sample standard deviation. Now, to construct the interval, we need X bar, because that's the center of the interval, right? And we're going to add a margin of error to get to the high side of the interval. We're going to subtract our calculated margin of error to get to the low side of the interval. And so our interval will look like this in the end. So the only thing we really have missing here is the critical value. And the critical value is determined by what confidence level we choose, okay? So I'm going to get the T distribution table and show that to you. Okay, so let's just make up a example. Let's say that we took a sample of salaries, right? And we found that the mean of the salaries of those professors was $60,000 with a standard deviation of $15,000. And we sampled 15 professors. All right. To get this critical value here, we need to know two things. One is how many degrees of freedom there are. And I will say directly, degrees of freedom here is the size of the sample minus 1. And your book has a greater explanation of what degrees of freedom really means, but it's not that important. So just go ahead and trust me. Degrees of freedom are the size of the sample minus 1. So there are 14 degrees of freedom. So I'm going to go to my table here. I'm going to go down to line 14. Then I have to consider what confidence level I have chosen. So let's say I want to be 90% confidence that the interval includes the true mean salary level of professors in my area. So that is a confidence level of 90%. So I go down this column, and there's my critical value, 1.761. Okay, so I now know this is 1.761, and I know that the standard deviation of my population, of my sample, was 15,000, and I know that I want to take the square root of the sample size, which is 15. Okay, and that formula is going to give me my margin of error. So over here on the side, I'm going to go ahead and do that. All right. So it was 1.761 times 15,000 divided by the square root of 15. Now I can put this in a line of arithmetic operation because multiplication and division have the same, they're equivalent in the order of operations, okay? But you might want to be careful about this. Some people would have done this first and then multiplied by the critical value. It will turn out to be the same in this case. Okay, so my margin of error is 6,820 I'm just going to say 32 because this is money, right? So I've gotten it down to cents. All right. Once I've calculated the margin of error, then again, the confidence interval goes from the center, which is X bar, minus E, up to the center plus E. So that would be on the low side, 60,000. And I'm doing that on my calculator over here, minus 6,820.32. So that is 53,179.68 up to the interval margin of error plus X bar, which is 66,820.32. Then our interpretation of this interval is very important because it tells us something about our expectation of the mean of the whole population. And what we would say is we are 90% confident. Now notice this 90% was what we chose. That's how we looked up a critical value. Okay, so we are 90% confident that the true mean salary is between $53,179.68 and $66,820.32. Okay, so again, that statement of interpretation includes the two endpoints, but it also says how certain we are about that outcome, right? If we had wanted to be 95% confident, it would have changed this. And we know already that it has to have widened the range of numbers, right? Because the more confident you want to be, the wider that range of numbers is going to be. So this is pretty easy to do by hand, okay? But I know that most of you won't do that. Now, there are videos, there are handouts, there's all sorts of stuff about how to do this in the course content. And since I get asked about this so often, don't forget that on D2L, sometimes you don't see everything. If at the bottom of your page it says load more, it means there is more content below there, okay? So especially for chapter 6, you need to hit that button and see more, because chapter 5 has quite a lot of content. It's in the same unit, so it takes up a lot of space. You often will need to hit this in order to see other things like the handouts and the videos and stuff. Okay, so let's say we wanted to do it with StatCrunch. I'm not going to go over the calculator instructions, even though they are on both a video and a handout in the course content. But here's what we would do if we want to do this in StatCrunch, okay? So it tells you again that you don't know the standard deviation of the population, right? And if you don't know it, which you don't, the population standard deviation, then you always choose t-stats. In this case, we actually skip 6.1, which is about using the z-stats when you know the standard deviation of the underlying population. So this is what is relevant for you. You choose t-stats, so you go to stat, and then you go down to t-stat, okay? And it opens up this window here. You choose one sample. You will never have paired samples or two samples in this introductory course. Then you go over, and normally you will choose with summary, okay? Which means you already know X bar, you know S, you know the sample size. That will bring up this window, and you will simply put in your sample mean, your sample standard deviation S, and your sample size. Then you'll need to click on this little circle to indicate that you want to do a confidence interval, and you need to make sure that this number for the confidence level matches what you were asked. Okay? So I want to do the problem that I just did by hand using StatCrunch. Okay, so now I need to change what I'm sharing, and I want to go to my screen. Okay, so now you should be seeing a StatCrunch window. Wait till it comes up. Okay, so I'm going to go to Stat, then I'm going to go down to, this was a means, t-stats, then over to one sample with a summary, and there's my box. So for my problem, the sample's mean was 60,000. The sample standard deviation was 15,000. The sample size was 15. Then I click on that circle to indicate I want to do a confidence interval, and I need to change to 0.90. And then I hit compute. Okay, and here is my interval. So notice that the lower side and the upper side are very slightly different from what we did by doing it by hand. That's going to be the thing most of the time because of the limitations in accuracy that you have when you use a critical value that comes from a table. Okay, here the critical value is more accurate. And so these two limits are very slightly different, but you can see that it is fundamentally, it's within $1 of each other on both sides. So this is the way you would do this kind of problem in StatCrunch. And I've got to say, you don't have to use StatCrunch. I've never required that, but it is very useful here because it automatically computes your margin of error right here, and it tells you the middle of the interval, that's your sample mean, and then it gives you the two endpoints. there's nothing to calculate here. If you use StatCrunch, it gives you everything that you might be asked in a problem. Okay, so let me go back to the presenter window, and let's talk about the other type of confidence interval that we want to compute in this chapter, and that is a proportions interval. Okay. It seems quite reluctant to go to the presenter window. There we go. Okay. Now, a proportions interval is done in the same basic way. The formula is different if you're doing it by hand, but it's fundamentally like what you did with the means interval. You have the same basic idea about what the interval is, but now the center of the interval here is actually the proportion from your sample, p hat. And the lower side is p hat minus the margin of error, and the upper side is p hat plus the margin of error. In that way, it's basically the same idea. Now, just like with the means, you need to be able to compute what the margin of error is. If you're doing it by hand, the formula is a z critical value times the square root of p hat, the proportion in your sample, q hat, which is, q hat is 1 minus p hat. So p hat and q hat always add up to 1, divided by the size of the sample. So that's your formula. So this critical value is exactly the same idea as the t critical value was for a means interval. So I'm going to actually look at a problem that is in your textbook. Okay, so it says use the following, the data in example 1 to construct a 95% confidence interval for the proportion of U.S. adults who use Facebook. Okay, so what this indicated was that in our problem, the data, p hat was 68%, which is 0.68. That's based on an estimate of 1,550 people. All right, and they told us that we wanted to be 95% confident. Now, a word about p hat. Sometimes we use old estimates for proportions that don't change much. But you have to be careful about that because there are some kinds of proportions that change very, very rapidly. So, for example, there were debates with Democratic candidates this past week. P hat, that estimator, changed a lot. The proportion of support for certain candidates will have changed a lot between last week and this week. So you just have to be careful and know when to take a new survey and re-estimate p hat. But anyway, we have the information we need. And again, what we envision is we want to be 95% confident, and we would like to know the z value that separates out this 95% confidence in the middle of a bell-shaped curve. Okay, now I'm not going to look that up. You can look it up on a normal distribution curve, but most of the time, and it is true for ours, they give you the most common ones down here. So we wanted to be 95% confident. That's a z value of 1.96. Okay, so let's compute the margin of error. So 1.96 times the square root of 0.68 times, and again, Q hat is 1 minus P hat, that's 0.32 divided by the square root, or sorry, divided by the size of the sample. So this is what we want to compute. Now, you can do that on a calculator pretty easily. So I'm going to go ahead and do that. And I'll go ahead, just because for a lot of people it's confusing, I'll go ahead and do this inside the square root first. So I'm just going to say 0.68 times 0.32 divide 1550, enter. And so this number is the result of this thing. What was it? 0.01184850061. And I wanted to multiply that by the 1.96. So times 0.96. Okay, so that is 0.023. And most of the time we just go to 3 decimal places. It was 223072, but this is close enough. All right, so and notice that is 1 more decimal place than P hat went to. That's kind of customary to go 1 more than the estimator. That would mean that the interval went from 0.68 minus 0.023 up to 0.68 plus 0.023. I can get the upper end pretty easy. Okay. The lower end is harder, but I believe it's 0.657 without using my calculator anyway. So what the interpretation here would be is that we are 95% confident that between 65.7% and 70.3% of adults, U.S. adults, use Facebook. Then notice that the interpretation is really critical to understanding what we're doing. First of all, we're telling you how confident we actually are. And then we're telling you the endpoints, but we're also telling you what those 2 endpoints represent, that they represent the percentage of U.S. adults that use Facebook. Okay? You have to make sure that every time you do an interpretation, you get in all 3 of those elements. Okay? So it ties it back into the purpose of doing the problem. So again, I don't expect you to do these by hand. So to do that on StatCrunch, there is, again, another handout about doing this in StatCrunch. I'm taking this directly from your course content. So you're going to go to Stat and then Proportion Stats, 1 sample, and then usually it's with summary, okay? And it'll pull up this window. So let's do this for this particular problem. All right, so I'm going to share the screen. Hopefully you're now seeing the screen. Okay, so I'm going to go to Stat. I'm going to go down to Proportion Stats, 1 sample with a summary. When I click it, it brings up this box. And so they asked me for number of successes. And notice we didn't really have that. What we had was the percentage. Now, number of successes would be the number of people in my original sample who said they use Facebook. So that was 1,550 times 0.68. That will give me 1,054. Now, I'll show that to you in just a minute, how I got that. I'll give you a little explicit formula for it. And so that was out of a sample size of 1550. I want to create a confidence interval. I did want to be 95% confident, so I don't need to change that. You can leave this at standard walled and hit compute. And so this is what I get. And notice that rounded to 3 decimal places, this is exactly the same upper and lower limits that we had previously. Okay, so let me go back to my presenter window, and I'll tell you how I got the 1054. The formula for p hat is always the number who gave the specific response we were interested in divided by the total number in the sample. Okay? But if what we're given is p hat and the size of the sample, and we want to know how many people gave a specific reply, which you do need if you're going to use the StatCrunch window, we can transform this algebraically to read the specific number equals p hat times the sample size. And that is what I did to get the 1054. I took 0.68, that was p hat, and I multiplied by 1550, and that's how I got 1054. Now, let me say explicitly that x must be a whole number. So it happened that this actually turns out to be an exact whole number, okay? But if it had not, you round to the nearest whole number, okay? It's important. If you try to put in a non-whole number in there, it will give you an error message. Okay, so that was section 6.3. Section 6.4 is omitted, but there is one further little deal which was in 6.3, and it's actually the very last part of 6.3 about estimating a minimum sample size. And again, there are 2 ways to do it. You can do it by hand, and you can do it using StatCrunch. And I'm going to show you how to do it by hand first. So we care about how large the sample has to be that we take. And it logically should seem appealing to you that if I want to be more confident, then logically I need to sample more people, right? So that seems appropriate, and that's actually true. And the thing about it is that the sampling process is the one big place where you spend a lot of money. It's hard to set up good samples. It's hard to perform the necessary work to get them. And so that's where you actually spend money when you do statistical estimations. So it turns out that the formula for finding a sample size estimate for a proportion is this. Now, that looks like magic. That is not magic. Remember what our formula for the actual margin of error was? That formula looked like this. Okay? Now, as an aside, since I realize now that I didn't say this, that little C there, any subscripted letter or number is just an indicator of which Z value, or it identifies an individual. So it doesn't have any place in a numerical formula, and I mean, you don't do anything with it. It's just an identifier, okay? So this is the critical value that reflects how confident we want to be. P hat is the proportion in the sample, Q hat is 1 minus P hat, and N is the size of the sample. But through the magic of algebra, notice what happens. And I'm just going to quickly do this. If I square both sides, I have E squared, Z squared, and when I square a square root, I just get whatever is inside the square root. That's what we call the argument of the square root. Okay. Now, there's the thing I'm interested in, the size of the sample, okay? So now I'm going to multiply both sides by the size of the sample. And over here, it'll cancel, okay? Now, I'm going to divide both sides by the square of the margin of error. And probably I should trying to save myself some writing, but that's silly. So I'm going to divide both sides by the square of the margin of error. And again, on the left, it's going to cancel, just leaving me in, okay, which is what I want. On the right, it leaves me with two things that are squared, the z critical value and the margin of error. So I'm going to put them together so they both get squared. And then p hat and q hat. And amazingly, that's my formula. So this was not magic. This formula was derived directly from the formula for calculating the margin of error in a proportions interval. Okay, so we can estimate what size sample we need if we get a desired confidence level, and the confidence level gives us this critical value, right? Just like what we did do. We also get to specify our margin of error. It's a choice here, right? Like say, I want to estimate within $50 the average cost of a used car or something. In any case, we get to choose how much error we are allowing, okay? If you were doing this in, say, a presidential poll, you know, you might have a relatively large margin of error for a long time while you know, getting your act together to run. But if it's 2 days from election day, you may want to have a sample that's accurate to a very, very fine degree, you know, has a very small margin of error. So this is a choice and confidence level is a choice, but your choices drive these two numbers. Then this is based upon either a prior estimate, or you can use the number 0.25, because it turns out that p hat times q hat, the largest it can ever be is 0.25. So you use a prior estimate when you think that estimate will be good, you know, in a situation where the p hat stays relatively constant. But if you don't have information, or if you think that p hat is changing rapidly, then you use 0.25 as the estimate of this product of p hat times q hat. Okay, so I'm going to look at example 2 on page 322 in your textbook. So, no, wait a minute. That's not the one I want. Okay, how about example 4 on page 324? So it says you're running a political campaign in which to estimate with 95% confidence the population proportion of registered voters who would vote for your candidate. Your estimate must be accurate within 3% of the population's proportion. So find the minimum sample size that is needed when you have a prior estimate that p hat is 31%, okay? So to do that problem, I need to read through it carefully and figure out what they're telling me. Okay, so they are telling me that they want to use a estimator of 31%, which is 0.31, right? Because we don't use percents in arithmetic operations or formulas. Okay, they also are telling me that we want to be 95% confident. 95% confident when you're talking about proportion means that I have a z critical value of 1.96. And again, see this little arrow that I use? It means that this in some way implies this other thing. So 95% confidence when I'm dealing with a proportion tells me I'm going to use a z-distribution table, and I'm going to choose the z-value for 95% confidence. So that's that little square table in the corner of the z tables. Okay, so that gives me another thing I need. It also tells me I am allowing myself a margin of error of no more than 3%. Well, 3% is 0.03. Okay. And that was in the thing that said your estimate must be accurate within 3%. Accuracy is the margin of error. Okay. So at this point, I have everything I need, because if p hat is 0.31, then q hat is 1 minus 0.31, which is 0.69. Okay? So n is equal to z over e squared times p hat times q hat. Okay, so that's 1.96 over 0.03 squared times 0.31 times 0.96. And I'm not going to do that on my calculator, but it turns out that that is 913.02. Now, n has to be a whole number, right? Because in fact, you can't ask questions of 2/100ths of a person. And you are tempted to use the arithmetic rounding rule of going to the nearest whole number. But the word that we used was minimum sample size. Minimum means you must round up. Unless it turns out to be an actual whole number, you round up. So my minimum sample size here is 914. Okay? So you can look at that problem on page 324, and I suggest you do. But most people now ask me, well, could I have done this on StatCrunch? Well, yes, you can. But it is not a very straightforward process. Okay? I'm going to show you how to do it, but again, it is not a straightforward process. Now, I have this handout that I'm showing you. It deals with both estimates when you're dealing with means and with proportions. But in fact, you're usually doing this with proportions. So let me show you how to do that by going to StatCrunch. So I'm going to share my screen. Okay, so you should be now looking at my screen. And then I'm going to go to Stat, down to Proportion Stats, because I was doing a problem around a proportions interval. And then I go to one sample, but now I'm going to go down to width/sample size. Okay, so it yields this box. Now, I know in my problem I wanted to be 95% confident, so I don't need to change the number inside this box. But target proportion you should read as p hat. So I do need to change that to 0.31. Then the other thing I have to do is define the width of the interval. Now, remember that to get an interval, you subtract p hat on the left side and you add, you subtract the margin of error on the left side and you add the margin of error on the right side. So the width of the interval is always 2 times the margin of error. In the problem that we just did by hand, the margin of error was 0.03, which is 3%, okay? So 2 times 0.03 is 0.06. And that's what you type into that. And then you hit compute, and notice this is its answer, 913. Okay, so when you're doing this thing with StatCrunch, you'll sometimes turn out to have a slightly different answer than what you get if you're doing it by hand. But you can still use this. The hardest thing for most people using StatCrunch to do a sample size estimator is to get this thing right. Okay? But you just have to remember that the width of the interval is always 2 times the margin of error. Full stop. Whether it's a means interval or it's a proportions interval, it doesn't matter. It's 2 times the margin of error. Okay? So I'm going to leave it to you to look at the example on page 324 about how to determine a minimum sample size when you do not have a useful prior estimate of the population proportion, p hat, okay? And that actually is all that we need to go over. So hopefully this will help you. I'm sitting here on Tuesday, July the 2nd, and your all's lab is due tonight. So I'm going to post this as quickly as I can. Okay.